Late Autumn 1943. Rechlin Lair's airfield, the secret heart of the Luftwaffe's technological empire. Inside a sterile, brightly lit office, Dr. Klaus Richter, chief of airframe analysis, stared at a combat report from Jagdgeschwader 26. His pencil hovered over a single perplexing detail. The report filed by an ace pilot after an engagement over the French coast was triumphant. Another American fighter, a lumbering Republic P-47 Thunderbolt, had been shot down. The pilot's commentary was filled with the casual arrogance of a predator who knows his prey intimately. He called it a Fliegender, Milchkrug, a flying milk jug, a fat, clumsy target that soaked up ammunition until it finally, reluctantly fell from the sky. This was the consensus in the Oberkommando der Luftwaffe, an opinion echoed in the ready rooms from the Pas de Calais to the Rhine. The P-47 Thunderbolt was an aeronautical joke, a 7-ton monument to American naivete. It couldn't turn with a Focke-Wulf, it couldn't climb with a Messerschmitt. It was by every metric of European air combat doctrine a catastrophic failure. Yet as Dr. Richter reviewed the growing file of wreckage analyses and after-action reports, a disturbing counter-narrative was beginning to emerge. The pilots saw weakness. Richter's engineers were finding something else entirely. The fragments of metal recovered from crash sites told a story not of fragility but of incomprehensible resilience. A wing spar from a P-47 shot down near Lille showed evidence of multiple 20mm cannon strikes, any one of which should have disintegrated the wing of a Bf-109. Instead, the American spar was merely mangled, its thick, forged aluminum stubbornly refusing to fail. Another report detailed a captured American pilot's debriefing. The fragments of metal recovered from crash sites told a story not of fragility but of incomprehensible resilience. A wing spar from a P-47 shot down near Lille showed evidence of multiple 20mm cannon strikes, any one of which should have disintegrated the wing of a Bf-109. Instead, the American spar was merely mangled, its thick forged aluminum stubbornly refusing to fail. Another report detailed a captured American pilot's debriefing. Their kill counts were climbing. The Americans were bleeding, losing pilots and machines at a rate that seemed on the surface unsustainable. The Luftwaffe believed they had the measure of this new American weapon. It was a bomber masquerading as a fighter, a flawed design born from a nation that understood mass production but not aerial combat. They were confident that tactics and superior pilot skill would always triumph over this brute force approach. But the numbers, the cold, hard engineering data whispered a different, more terrifying truth. The aircraft were falling, yes, but they were not breaking apart in the sky. They were being beaten to death, absorbing levels of punishment that defied German understanding of structural mechanics. Through the laboratory windows, Richter could see the smoke rising from the factories across Germany, tangible evidence of the Allied bombing campaign, a campaign that was growing more intense, more accurate, and more devastating with each passing week. That campaign was being escorted by these very fighters the aces dismissed. And here in his quiet office lay physical proof that the technological and industrial reality was far more complex than anyone in the German high command dared to admit. The American approach wasn't elegant. It was crude, heavy, almost insulting in its lack of finesse. Where German designers shaved off every possible gram to achieve peak performance, American engineers seemed to have added armor and reinforced structures with reckless abandon. Where a Messerschmitt was a scalpel, the Thunderbolt was a sledgehammer. What neither Richter nor his colleagues yet understood was that this growing file of contradictory evidence was the prelude to a revelation that would shatter their most fundamental assumptions about warfare. They were witnessing the first signs of a clash between two worlds, the world of exquisite, high-performance craftsmanship and the world of overwhelming, indomitable industrial might. The pilots saw a clumsy victim, but the engineers were beginning to suspect they were looking at the ghost of an entirely new kind of predator, one that didn't play by their rules. The mathematics of German victory were being written in kill ratios and tactical brilliance. But the mathematical certainty of their defeat was being forged not in elegant dogfights, but in the cold hard physics of structural endurance and the terrifying logic of the Detroit assembly line. A logic they couldn't yet comprehend, but one they would soon be forced to confront firsthand. The discrepancy was too great to ignore. A single intact specimen would be needed to solve the riddle of the flying milk jug to understand if it was truly a blunder or a monster in disguise. The search for that specimen was already underway, a top priority for Luftwaffe intelligence. Little did they know, their prize was already flying its pilot, unaware that a single wrong turn or a moment of mechanical failure would deliver the key to this terrifying mystery directly into their hands. That moment would force Germany's finest engineering minds to admit they were facing a power unlike anything they had ever seen. The story of that discovery of the secrets they unlocked inside that captured machine is a lesson in how arrogance can blind even the most brilliant minds to the nature of their own destruction. To make sure you don't miss that revelation, take a moment to subscribe to our channel and hit the notification bell. You won't want to miss how this story unfolds. He claimed his aircraft had absorbed over 200 machine gun rounds and 5 cannon hits before the engine finally gave out. The German intelligence officer had dismissed it as Yankee bravado, but the physical evidence landing on Richter's desk suggested the American wasn't lying. The disconnect was maddening. On one hand, you had Germany's finest aces, men like Josef Pips Priller, laughing as they described these fat targets that flew like freight trains. Army Air Corps issued its requirement for a new interceptor in 1940. The specifications were demanding, but still rooted in the traditional fighter philosophy of agility and speed. Kartveli took one look at the requirement for the new Pratt & Whitney R2800 double wasp engine, a colossal 18-cylinder air-cooled radial powerhouse, and understood that traditional philosophy was obsolete. He famously told his design team, "It will be a dinosaur, but a dinosaur with good proportions." He wasn't building a duelist rapier, he was forging a barbarian's broadsword. This design philosophy was the antithesis of everything German engineering held sacred. Men like Willy Messerschmitt and Kurt Tank were artists of aerodynamics. Their creations, the Bf 109 and Fu 190, were lightweight, responsive, and optimized for a single purpose: to give a skilled pilot the ultimate advantage in a turning, climbing dogfight. They were built around powerful liquid-cooled inline engines like the Daimler-Benz DB605 engines that were marvels of compact, high-performance engineering. Every component was meticulously crafted to save weight, to reduce drag, to create a machine that was an extension of the pilot's own will. The German approach was to build the perfect weapon for the perfect pilot. Kartveli's approach was to build a survivable platform for a devastating weapon system and to ensure it could be built by the tens of thousands. The core of the P-47's design was not the airframe, but the systems it was built to carry. First was the R2800 engine, a monster that weighed over a ton by itself. An air-cooled radial engine by its very nature was more resilient than a liquid-cooled one. It had no vulnerable radiators, no fragile coolant lines to be severed by a single stray bullet. It could sustain immense damage, lose entire cylinders, and still have enough power to drag the shattered airframe home. But this engine demanded a huge fuselage to house it, creating immense drag. To overcome this, Kartveli needed even more power, especially at high altitude where the bombers would fly. The answer was a technology Germany knew of but had deemed too impractical for a single-engine fighter: the turbo supercharger. This complex system, which used hot exhaust gases to spin a turbine that compressed intake air, was heavy, complicated, and required extensive, bulky ductwork. Kartveli's solution was audacious. He placed the entire turbo unit deep in the rear fuselage and ran the enormous ducts along the bottom and sides of the cockpit. This decision dictated the Thunderbolt's iconic barrel-shaped fuselage. It was a design driven not by aerodynamics, but by plumbing. The result was an aircraft that horrified even its own pilots at first. The 56th Fighter Group, the first unit to receive the P-47, suffered a terrifying string of training accidents. Between January and August of 1942, they lost more pilots in training than they would to the enemy in their first few months of combat. The plane's immense torque could flip it over on takeoff. Its high landing speed made it a nightmare on short runways. And in a dive, it could encounter a terrifying phenomenon called compressibility, where shock waves formed on the wings, freezing the controls and sending the plane into an unrecoverable plunge. Many American pilots, much like their German counterparts, initially hated and feared the machine. They called it the Jug, not just for its shape, but because it felt as agile as one. They yearned for the nimble Spitfires, the RAF flew fighters that felt alive in their hands. The Thunderbolt didn't feel alive. It felt like a force of nature, a barely tamed beast that was just as likely to kill its master as the enemy. This was the context behind the German aces' initial mockery. They weren't just being arrogant, their assessment was by all conventional measures correct. The P-47 was a poor dogfighter. It was a sluggish climber at low altitudes, But German intelligence failed to grasp the fundamental shift in doctrine the aircraft represented. They were judging a battering ram by its ability to fence. They saw the weight, the drag, the sheer brute force as design flaws. They couldn't conceive that these were in fact intentional features of a new kind of war, a war of attrition, energy, and overwhelming firepower. The engineers at Rechlin, however, were not pilots. They were men of science, trained to look past the performance envelope and into the soul of the machine. As they pieced together the evidence from shattered wings and mangled fuselages, they saw the method in the madness. They saw the oversized structural members, the redundant control systems, the sheer mass of metal dedicated to protecting the pilot and critical components. The fragmented reports were painting a picture of an aircraft that was not designed to outturn the enemy, but to outlive them. And to do that, it had to bring its own secret weapon to bear, a weapon that was only effective if the plane could survive long enough to use it. The engineers knew they could not solve this riddle with mere scraps of metal. The whispers from the wreckage were becoming a roar, and they needed to hear what the beast itself had to say. The wreckage analysis sheds at Rechlin were cathedrals of reverse engineering. Here, under the harsh glare of industrial lighting, fragments of downed Allied aircraft were laid out on vast concrete floors like the bones of prehistoric beasts. Teams of specialists would descend upon the metallic carcasses, their task to dissect, document, and ultimately understand the enemy's mind through the artifacts of his creation. By late 1943, the sheds were filled with the familiar shapes of Spitfires, Lancasters, and B-17 seconds. German engineers knew these machines intimately. They respected their quality and capabilities, but they found no fundamental surprises. The British designs were elegant, a product of a long and storied aeronautical tradition. The American bombers were robust and practical, but they all spoke a language of engineering that the Germans understood. The P-47 Thunderbolt, however, was speaking in a foreign dialect. Dr. Richter and his team moved among the Thunderbolt fragments with a growing sense of unease. Every piece they examined contradicted their expectations. Take the riveting, for example. German airframes used flush-headed rivets, a time-consuming but aerodynamically clean process. The P-47 fragments were covered in round-headed rivets, a method that was faster and stronger but created more drag. To a German designer, it was a mark of crude, lazy construction. But a metallurgist on Richter's team pointed out that the alloy used in the American rivets was of a remarkably high consistent quality, suggesting a mastery of mass production that Germany could no longer take for granted. Then there was the wiring. In a German fighter, the electrical loom was a bespoke creation, carefully fitted by skilled artisans. In the P-47 wreckage, they found standardized wiring harnesses. Each wire was color-coded and stamped with a part number, part of a modular system designed for rapid assembly and repair. An electrician could replace an entire section in minutes, whereas a similar repair on a Focke-Wulf could take hours. It was the logic of a Detroit auto plant, not an aircraft manufactory. The sheer mass of the components was staggering. They examined a landing gear strut that was thicker and heavier than one from a Ju-88 medium bomber. The pilot's seat was a cocoon of steel armor plate with another thick slab behind his head and shoulders. They calculated that the armor protecting the P-47 pilot weighed more than the entire cannon armament of a Bf-109. This was not a fighter, it was a flying armored car. The philosophy was clear. The pilot was the most valuable component of the weapon system, a precious resource to be protected at all costs. This contrasted sharply with the Luftwaffe's increasingly desperate reality, where experienced pilots were becoming an endangered species. The Americans were building their machines with the assumption that their pilots would be hit, and they were engineering them to bring those pilots home anyway. But the greatest mystery lay in the heart of the wreckage, the fragments of the Pratt & Whitney R-2800. German engineers were masters of the liquid-cooled V-12 engine. The DB-605 and Jumo-213 were compact, powerful, and aerodynamically sleek. They viewed the air-cooled radial engine as an obsolete, brute, inefficient, drag-inducing, and suitable only for bombers and transport planes. Yet the evidence from the field was undeniable. These engines were absorbing unbelievable punishment. They found R-2800 crankcases with holes punched clean through them. Cylinders with pistons seized solid. Yet, the combat reports indicated these engines had often continued to run, sputtering and shaking, but generating enough power for the pilot to escape. The radial engine had no vulnerable cooling system to fail. Its sheer size meant that damage to one part of the engine often didn't affect the rest. It was a remarkably simple, almost agricultural piece of machinery compared to the high-strung thoroughbreds built by Daimler-Benz. But in the brutal calculus of combat, its resilience was proving to be a decisive tactical advantage. The engineers at Rechlin were beginning to understand they were not looking at an inferior design, but a different design, born from a different set of priorities. German engineering sought peak performance. American engineering sought relentless, repeatable reliability. German doctrine relied on the skill of the ace to avoid getting hit. American doctrine assumed the pilot would be hit and relied on the machine to endure it. These whispers from the wreckage were coalescing into a single, terrifying conclusion. America was waging war with a different set of rules written not by fighter pilots, but by industrial engineers. The P-47 wasn't a mistake. It was a statement of intent. It was the physical manifestation of a strategy that intended to win not by outdueling the Luftwaffe, but by outproducing, outlasting, and ultimately crushing it under an avalanche of steel. Richter knew his analysis would be met with skepticism, even ridicule by the fighter aces and their patrons in the high command. He needed more than fragments and theories. He needed the whole machine intact and operational. A message was circulated to all frontline intelligence units. The capture of a flyable P-47 Thunderbolt was now a matter of the highest national priority. They had to understand the beast before it devoured them completely. The opportunity the German high command so desperately sought came not as the result of a daring commando raid or a brilliant aerial victory, but through the mundane, unpredictable chaos of war. On le 19 novembre 1943, descendait Lieutenant William J. Miller of the 78th Fighter Group lifted his P-47C Thunderbolt off the runway at RAF Duxford. His mission was a high-altitude escort for B-17 bombers, striking a target near Gelsenkirchen in the industrial Ruhr Valley. Miller was a relatively new pilot on only his 5th combat mission, still learning the complex relationship between his heavy fighter and the unforgiving European weather. The mission started as planned, a long grinding climb to 2,800 feet, the bombers, a sprawling constellation of silver, ahead the Thunderbolts weaving a protective screen around them. But as they crossed into German airspace, two enemies attacked simultaneously, the Luftwaffe and the weather. A wave of few 190 seconds tore into the formation, and the sky erupted into a chaotic ballet of diving fighters and defensive fire. In the swirling confusion of the dogfight, Miller became separated from his flight. He chased a German fighter down through a thick bank of clouds, fired a burst, saw no result, and pulled up disoriented. The sky that had been filled with hundreds of aircraft was now empty. Below him was a solid, impenetrable blanket of gray cloud. His radio crackled with static. He was alone somewhere over the heart of the Third Reich. Standard procedure was to climb above the clouds and take a heading west toward England, trusting his compass and his fuel gauge. But as he climbed, his engine began to run rough. A film of oil started to coat his windscreen. The R-2800, for all its legendary durability, was not infallible, and a minor oil line leak at altitude could quickly become a critical failure. With his engine vibrating and his visibility forward obscured, Miller made a fateful decision. He would descend through the cloud cover and try to get his bearings, hoping to find a landmark to guide him home. He began a slow, careful descent, his eyes glued to his instruments. He broke through the base of the clouds at around 3,000 feet and found himself not over the fields of France or Belgium, but over a landscape dotted with the distinctive red-tiled roofs of Germany, and directly ahead, nestled in a clearing, was an airfield. It looked small, a secondary training field perhaps. He saw what appeared to be several Fiesel or Storch observation planes parked near a hangar. In his stressed and disoriented state, he made a catastrophic assumption he must be over Allied-occupied territory, perhaps a freshly captured forward airstrip. With his fuel running low and his engine threatening to seize landing, was his only option. On the ground at a Luftwaffe training field near Münster, the German personnel stared in stunned disbelief. A P-47 Thunderbolt, the fat American fighter they had only seen in recognition manuals, was circling their airfield, its landing gear down. At first, they thought it was a trick, a prelude to a strafing run. The anti-aircraft crews scrambled to their guns. But then the plane's landing flaps deployed, and it began a textbook approach. The flak commander, a veteran officer, made a split-second decision that would change the course of German aviation research. He ordered his men to hold their fire. The potential intelligence windfall from a captured intact aircraft was infinitely more valuable than another kill marking on a gun barrel. Miller brought the big fighter in for a surprisingly smooth landing on the grass runway. As he rolled to a stop and cut the engine, he likely felt a wave of relief. He had made it. He was safe. The relief lasted only until he saw the vehicles racing towards him across the field, not American Jeeps, but German Kübelwagons, filled with soldiers in the field gray uniforms of the Wehrmacht. The sickening realization hit him with the force of a physical blow. He had just delivered one of America's most advanced weapons directly into the hands of the enemy. Within minutes, he was surrounded a prisoner of war, but the Germans were far less interested in the pilot than they were in his machine. A jubilant, almost frantic message was flashed to the highest levels of the Luftwaffe High Command in Berlin. The specimen had arrived. The flying milk jug had come home to roost. For the engineers at Rechlin, it was as if Christmas had come a month early. The whispers from the wreckage could finally be silenced, replaced by the hard, undeniable voice of the machine itself. The journey of Lieutenant Miller's captured Thunderbolt to the heart of the Reich's research establishment would be one of the most secret and urgent logistical operations the Luftwaffe had undertaken in months. For this was not merely a captured aircraft. It was a key that could unlock the terrifying truth of America's industrial war machine. The capture of Lieutenant Miller's P-47 triggered a flurry of activity that rippled from the quiet training field in Münster all the way to the Reich Air Ministry in Berlin. This was not a routine intelligence matter. It was a strategic event of the highest order. The order from Generalfeldmarschall Erhard Milch's office was unequivocal. The aircraft was to be secured, concealed, and transported to the Erprobungsstelle Rechlin with the utmost speed and secrecy. A team of specialist engineers from Rechlin itself was dispatched immediately, not just to inspect the prize, but to oversee its disassembly and transport. They arrived within hours, their excitement barely concealed beneath a veneer of professional detachment. They were about to perform an autopsy on a living creature. The first step was to make the aircraft disappear. Before Allied reconnaissance aircraft could spot the distinctive silhouette of the Thunderbolt on a German airfield, a sight that would have triggered an immediate and massive bombing raid, the P-47 was hastily towed into the largest hangar. Armed guards were posted at every entrance with orders to shoot anyone who approached without the highest level of clearance. The team of engineers, led by a stern, methodical man named Dr. Hans-Georg Schmid, began their preliminary examination. They walked around the machine in reverent silence, their hands tracing its contours. Up close, the Thunderbolt was even more intimidating than the report suggested. It was brutally functional. The round-headed rivets that looked crude in photographs now seemed like unapologetic statements of strength. The massive landing gear struts looked like they belonged on a bomber. And the engine cowling housed the R-2800 like a shrine to pure, unadulterated power. Disassembling an aircraft of this size for transport was a monumental task. The German team worked with a surgeon's precision, meticulously documenting every step. They were not merely taking it apart, they were learning from it. They noted the American use of standardized fasteners, which made disassembly far quicker than on a German plane. They marveled at the accessibility of key components, a design feature that spoke to a philosophy of rapid field maintenance. A Focke-Wulf was a masterpiece of integrated design, but a nightmare to repair. The Thunderbolt was built like a tractor, with the assumption that parts would fail and would need to be replaced quickly by mechanics with limited training. After 3 days of intense, around-the-clock work, the aircraft was reduced to its primary components: the fuselage, the two wings, the tail assembly, and the engine, which was carefully cradled in a specially constructed transport rig. The journey to Rechlin, over 200 miles to the northeast, was a masterpiece of wartime logistics and deception. The convoy consisted of 3 massive flatbed trucks, each carrying a piece of the American Giant, and a heavily armed escort of half-tracks and motorcycle outriders. The components were shrouded in thick canvas tarpaulins, disguising their shape from prying eyes on the ground or in the air. The convoy moved only at night, navigating a circuitous route along secondary roads to avoid major cities and Allied air patrols. For the German soldiers guarding the strange, oversized cargo, it was a nerve-wracking journey through their own homeland, a land now stalked by the constant threat of Allied fighter bombers, Jabos, many of which were P-47 seconds. The very same type of machine they were so carefully concealing. The irony was not lost on them. Finally, in the pre-dawn hours of November 26th, the convoy rolled through the heavily guarded gates of the Rechlin Test Center. The components were taken directly to Hangar 5, a secure facility reserved for the analysis of captured enemy technology. As the tarpaulins were pulled back under the bright hangar lights, the full scope of their prize was revealed to the assembled leadership of the Luftwaffe's technical branch. Here, laid out in pieces, was the answer to the riddle that had been plaguing them for months. It looked less like a fighter and more like a collection of industrial machinery. It lacked the aesthetic grace of a Spitfire or the predatory elegance of a Focke-Wulf. It was blunt, oversized, and unapologetically American. Dr. Richter, who had flown in from Berlin to oversee the project, stood before the fuselage, his mind racing. The pilots had called it a milk jug. Looking at the sheer, unadorned bulk of it, he could see why. But he also knew that within this ugly utilitarian shell lay the secrets to America's growing dominance in the air. The hangar doors boomed shut, sealing the engineers inside with their subject. The preliminary examination was over. Now the real work, the deep invasive autopsy of the juggernaut, was about to begin. Every rivet, every wire, every casting would be scrutinized, and what they would find would challenge the very foundations of German engineering pride. Inside the sterile confines of Hangar 5, an atmosphere of intense, almost religious concentration descended. The P-47's components, laid out like offerings on an altar of science, were subjected to a level of scrutiny that bordered on the obsessive. This was the German engineering method at its peak, methodical, precise, and exhaustively thorough. Every single part was to be weighed, measured, chemically analyzed, and its design philosophy reverse-engineered. The process began with the airframe itself, and the first revelation was one of pure, unadulterated mass. The engineers knew the Thunderbolt was heavy, but the raw numbers from their own scales were still shocking. The empty weight of the airframe, without engine, weapons, or fuel, was nearly double that of a Bf-109G. They were analyzing a fighter that weighed as much as a light bomber. The source of this weight became immediately apparent as they began to examine the internal structure. The main wing spar was a masterpiece of brute force engineering. It was a single massive beam of forged aluminum alloy, so thick and robust that the engineers initially mistook it for a component from a four-engine bomber. Their stress analysis calculations produced results that seemed impossible. The wing was designed to withstand G-forces far beyond the physical limits of any human pilot and far beyond what was necessary for conventional combat maneuvers. This explained the reports of P-47 seconds pulling out of vertical dives at speeds that would have ripped the wings off any German fighter. The Americans hadn't designed a wing for dogfighting. They had designed a wing to serve as a stable, indestructible gun platform and a diving battering ram. It was a structure built not to dodge blows, but to withstand them. Then came the armor. The engineers carefully unbolted the pilot's protection. The steel plate behind the seat was over half an inch thick, made of a high-quality hardened steel that their tests showed could defeat a 20mm cannon shell at all, but the closest ranges. The armored headrests, the deflection plates around the engine oil coolers, the bulletproof glass of the windscreen, it all added up to nearly 1,000 pounds of protection. It was a flying fortress built for a crew of one. A German pilot was protected by his skill and the agility of his aircraft. An American pilot was protected by a literal wall of steel. This discovery had a chilling psychological effect on the engineering team. It suggested a level of respect for the individual pilot and a willingness to sacrifice performance for survivability that was utterly alien to the high-command-driven victory-at-all-costs mentality of the Third Reich. America could afford to build heavy fighters because it valued its trained pilots so highly. Germany, burning through its veteran aces at an alarming rate, could not. The examination of the fuel tanks revealed another layer of American industrial ingenuity. The Germans were familiar with self-sealing fuel tanks, but the American version was on another level. It wasn't a simple rubber bladder. It was a complex, multi-layered sandwich of synthetic rubbers and treated fabrics. When punctured, the inner layer would swell upon contact with gasoline, sealing the hole while a tougher outer layer provided structural integrity. The team conducted a live-fire test on a sample section, firing their standard 7.92mm incendiary rounds into it. The holes sealed themselves in seconds, with only a brief, quickly extinguished flicker of flame. The system was not just effective, it was mass-producible. The materials, while advanced, were not exotic. It was a solution born from the massive American chemical industry, an industry that dwarfed Germany's own. Everywhere they looked, they found the same philosophy: simplicity, strength, and serviceability. Where a German design might use a complex, lightweight forging, the P-47 used a heavier but simpler casting. Where the FOR-190 had an ingenious but complex single-lever command system that automated engine controls, the P-47 had a bewildering array of manual levers and switches in the cockpit. The Germans initially saw this as a sign of inferior technology, but one of their test pilots, brought in to evaluate the cockpit layout, offered a different perspective. "It's complicated," he admitted, "but nothing is hidden. Every system is independent. If one fails, the others continue to function. In my 190, if the commando Gerät fails, I'm a glider. Here, the pilot can manually compensate for almost any failure." It was a design that trusted the pilot's skill not to perform elegant maneuvers, but to manage a complex machine under duress. The skin of the beast had revealed a philosophy of survivability. The cockpit hinted at a doctrine of redundancy and manual control, but the engineers knew the true secrets were still hidden. They had examined the bones and the armor, but now they had to confront the heart and soul of the machine, the massive radial engine and the mysterious ductwork that snaked through the fuselage, a system that held the key to the Thunderbolt's terrifying performance where the air was thin and German fighters struggled to breathe. With the airframe analysis yielding one shock after another, the engineering team turned its attention to the centerpiece of the Thunderbolt's design, the Pratt & Whitney R2800 double wasp engine. It sat on a heavy-duty test stand in the center of the hangar, stripped of its cowling, looking less like an aircraft engine and more like a piece of industrial art. For the German engineers who had dedicated their careers to perfecting the liquid-cooled inline V12, the R2800 was an object of both fascination and professional disdain. It was a relic, a throwback to an earlier era of aviation. It was huge, heavy, and created enormous aerodynamic drag. By all their metrics, it was the wrong choice for a high-performance fighter. Their task was to understand why the Americans had not only chosen it, but built their entire aircraft around it. The process of removing the engine from the fuselage had been their first lesson. It was mounted on a simple, incredibly rugged ring attached to the firewall by just 4 massive bolts. The entire engine, propeller, and all could be detached and replaced as a single unit in a matter of hours. This power egg concept was a revelation. A German fighter with a damaged engine was often out of action for days, sometimes weeks, as mechanics painstakingly worked in the cramped confines of the airframe. The American approach was different. Don't repair the engine in the field, just swap it out for a new one and send the damaged unit back to a specialized depot for overhaul. It was a philosophy that could only exist in a nation with a surplus of both engines and mechanics. It was the logic of a disposable society applied with terrifying efficiency to the art of war. As they began the teardown of the engine itself, their preconceived notions were systematically dismantled. The construction was deceptively simple. The 18 cylinders were arranged in 2 rows of 9, their cooling fins exposed directly to the air. There was no complex radiator system, no vulnerable coolant pumps or hoses, no reservoir of glycol that could leak out from a single shrapnel hit and cause the engine to seize in minutes. The Germans calculated that nearly 30% of their fighter losses in combat were due to failures in the liquid cooling system, often from minor damage that left the rest of the engine untouched. The R2800 simply eliminated that entire point of failure. Its ability to absorb damage was not a myth. It was a fundamental design feature. They examined cylinders that showed evidence of having been hit in combat on previously downed aircraft, yet the engine had continued to function. The sheer redundancy of having 18 cylinders meant that the loss of 1 or even 2 was not necessarily catastrophic. When they ran the captured engine on a test stand, the experience was visceral. The double wasp didn't hum with the high-strung precision of a Daimler-Benz. It roared. It was a deep, guttural, earth-shaking sound of raw, untamed power. The torque was so immense that it threatened to tear the engine from its heavily anchored mount. The specifications were already known to them, 2000 horsepower, but seeing it, hearing it, feeling it in their bones was something else entirely. Their own DB605, a magnificent engine, produced around 1475 horsepower. The American engine produced over 500 more horsepower, and it did so with what the Germans considered to be a cruder, less efficient design. They analyzed the metallurgy of the pistons, the crankcase, the cylinder heads. The quality of the alloys was superb, a testament to America's unrestricted access to strategic materials like nickel and chromium, which were becoming critically scarce in Germany. But the most humbling discovery was the manufacturing quality. Despite being a mass-produced unit, the internal tolerances were as fine as anything they produced in their own factories. The components were interchangeable between different engines, a level of standardization that German industry, with its reliance on skilled manual fitting, could not hope to match on such a scale. The R2800 wasn't a single masterpiece. It was one of over 1,2,5,000 identical masterpieces pouring out of American factories with a speed and consistency that defied belief. The engineers at Rechlin were forced to confront a painful truth. They had sneered at the American radial engine as a primitive brute, but they now understood it was a war-winning weapon, a symbol of a different kind of engineering genius, one that prioritized resilience over elegance, reliability over peak performance, and replaceability over reparability. It was the perfect engine for a war of attrition. But as powerful as the engine was, it alone could not explain the P-47's lethal performance at high altitude. The key to that mystery lay not in the front of the aircraft, but in the strange, complex system of pipes and machinery hidden deep in its belly, a system that would prove to be the most shocking revelation of all. With the R2800 engine's secrets laid bare, Dr. Richter's team turned their focus to the most unconventional aspect of the P-47's design, the labyrinth of large-diameter ducts that ran from the engine along the belly of the fuselage to a mysterious collection of machinery located behind the pilot's seat. In any conventional fighter, this space would be used for fuel tanks or radio equipment. In the Thunderbolt, it was occupied by a system that would prove to be the technological key to the entire aircraft and a source of profound despair for the German engineers who discovered it. This was the General Electric Type B turbo supercharger system, and it was a masterpiece of industrial engineering that Germany simply could not replicate. The concept of a turbo supercharger was not new. German engineers had experimented with the technology for years. It was a theoretically brilliant solution to the problem of high-altitude performance, used the energy of the hot, expanding exhaust gases energy that was normally wasted to spin a turbine. This turbine in turn drives a centrifugal compressor that crams dense pressurized air into the engine's intake, allowing it to maintain sea-level power even in the thin atmosphere of the stratosphere. The problem was that the practical engineering challenges were immense. The turbine wheel had to spin at over 2,000 revolutions per minute while being blasted by exhaust gases at temperatures exceeding 1,000 degrees Celsius. This required incredibly advanced alloys materials that could withstand extreme heat and centrifugal forces without warping or disintegrating. Germany's own research programs had concluded that while the technology was feasible for large, multi-engine bombers, where weight was less of a concern, it was too heavy, too complex, and required too many strategically vital rare metals, like cobalt, nickel, and tungsten, to be practical for a mass-produced single-engine fighter. They had abandoned the idea, opting instead for more conventional, mechanically driven superchargers. As the German team carefully disassembled the Thunderbolt's turbo system, they realized the Americans had not just solved these problems, they had industrialized the solution. The turbine blades were forged from a nickel-cobalt-chromium alloy of a quality and purity that Germany's resource-starved industry could only dream of. The intricate system of intercoolers which cooled the compressed air before it entered the engine to increase its density was a marvel of efficient, lightweight heat exchange. The entire system was regulated by a complex yet robust automatic control unit that adjusted the turbo's output to maintain optimal engine performance across a wide range of altitudes. It was this system that gave the P-47 its decisive advantage. While German fighters like the FOR 190, equipped with two-speed mechanical superchargers, began to lose significant power above 2,500 feet, the P-47's turbo allowed the R2800 to maintain its full 2,000 horsepower all the way up to 3,000 feet. In the high-altitude arenas where the heavy bombers flew, the Thunderbolt was not just a competitor, it was king. The German aces who had mocked the milk jug for its sluggish climb at low altitude had been ambushed in the stratosphere by a machine that was suddenly more powerful and faster than their own. The psychological impact of this discovery on the Rechlin team cannot be overstated. It was a moment of genuine technological shock. They were looking at a capability that they had personally deemed impossible to mass produce, and the Americans were fitting it as standard equipment on thousands of fighters. It explained everything: the P-47's ability to escort bombers at extreme altitudes, its astonishing diving speed that began in the thin upper air, and its ability to regain energy after a dive with a zoom climb that left German fighters struggling far below. The extensive ductwork was no longer a sign of crude design. It was the circulatory system of a high-altitude predator. The barrel-shaped fuselage was not a flaw. It was the necessary vessel for a war-winning piece of technology. Dr. Schmid, the lead engineer on the project, convened a meeting with his top analysts. The mood was somber. "It is not a matter of a single component," he stated, his voice heavy with the weight of his findings. "It is the entire system. To replicate this, we would need not only the designs, but also their foundries, their chemical plants, their machine tools. We would need their access to nickel and cobalt. We are not facing a superior aircraft. We are facing a superior industrial ecosystem." The admission hung in the air, a tacit acknowledgement of a war that was being lost not on the battlefield, but on the factory floor. They now understood the source of the Thunderbolt's power and the secret to its high-altitude dominance. But another piece of the puzzle remained, one that spoke not of potential energy and atmospheric physics, but of pure kinetic violence. They still had to analyze the reason for the Thunderbolt's existence, its weapons. They were about to dissect the components of a flying buzzsaw. Having uncovered the secrets of the Thunderbolt's survivability and its high-altitude heart, the Rechlin engineers turned their attention to its teeth. To the uninitiated, the P-47's armament seemed like a step backward. While the Luftwaffe had embraced the hard-hitting explosive power of 20mm and 30mm cannons, the Americans had stubbornly clung to the heavy machine gun. The Thunderbolt carried no cannons at all. Instead, its wings housed a fearsome battery of 8 50-caliber Browning M2 machine guns, 4 in each wing. To the German pilots who were accustomed to the decisive, destructive impact of a single cannon shell, this seemed like an inferior choice. A machine gun, even a heavy one, required multiple hits to bring down a sturdy aircraft. But as with every other aspect of the Thunderbolt, the engineers discovered that the American approach was rooted in a different and terrifyingly effective combat philosophy. They removed the guns from the wings, laying them out on long workbenches. The Browning M2, or Ma-Deuce, as it was nicknamed by American troops, was not a new weapon. It was a design that dated back to the end of the First World War, a testament to the genius of John Browning. But the version in the P-47 was a highly refined aircraft-specific model. It was reliable, rugged, and capable of a sustained rate of fire of around 800 rounds per minute. The engineers admired its simple, powerful mechanism. It was a weapon built to work every time in the freezing cold of high altitude and under the strain of high-G maneuvers. Then they did the math, and the true horror of the American design became clear. With 8 guns firing simultaneously, the P-47 produced a combined rate of fire of over 6,400 rounds per minute. That was more than 100 projectiles leaving the barrels every single second. A German pilot flying an FW-190 had 4 20mm cannons and 2 machine guns, a formidable armament. But his cannons carried only a limited amount of ammunition, typically around 200 rounds per gun, enough for only a few short bursts. The P-47, by contrast, carried a staggering 425 rounds for each of its 8 guns, for a total of 3,400 rounds. This gave the American pilot over 30 seconds of continuous firing time, an absolute eternity in a dogfight. The German pilot had to be a marksman, making every cannon shell count. The American pilot didn't need to be a marksman, he just needed to point his aircraft in the general direction of the enemy and hold down the trigger. The engineers calculated the weight of fire. A 1-second burst from the P-47's guns hurled approximately 12 pounds of lead and steel at a target. The projectiles, a mix of armor-piercing, incendiary, and tracer rounds, created a dense, inescapable cone of destruction. They studied the gun synchronization, noting how the guns were angled to converge at a specific point in front of the aircraft, typically around 300 yards. At this range, any aircraft unlucky enough to fly through the convergence zone would be hit not by 1 or 2 projectiles, but by dozens simultaneously. The effect was not one of penetration, but of annihilation. It was like a flying shotgun. The combat reports from German pilots suddenly made perfect sense. The descriptions of enemy aircraft simply coming apart or disintegrating in mid-air were not exaggerations. The concentrated stream of heavy-caliber bullets acted like a high-pressure water jet on a sandcastle, literally shredding aluminum skin, severing control cables, and shattering engine components. This analysis revealed the final piece of the Thunderbolt's tactical doctrine. It was an energy fighter. It would use its superior high-altitude performance and diving speed to position itself for a single devastating pass. It would not engage in a turning fight, it would dive fire a 2 to 3 second burst of overwhelming firepower and then use its momentum to zoom, climb back to safety, leaving a shattered wreck in its wake. It was a cold mathematical approach to air combat. The Germans called this weapon system Roosevelt's Kreissäge, Roosevelt's buzzsaw. The name was apt. It captured the mechanical, impersonal, and unstoppable nature of the destruction it wrought. The engineers realized the entire aircraft, its armor, its rugged engine, its turbo supercharger was designed with one purpose in mind: to deliver this buzzsaw to the target, allow it to do its work, and bring the pilot home to do it again. The next day, they had dissected the weapon and now understood its terrible power. But in the process, they had stumbled upon an even more profound and disturbing discovery, one that had nothing to do with technology and everything to do with the very soul of the nation that had built it. As the last components of the captured Thunderbolt were analyzed and cataloged, Dr. Richter and his senior engineers gathered in a conference room in Hangar 5. The walls were covered with blueprints. They had painstakingly created chemical analysis reports and performance charts. They had dissected the beast, and they understood its anatomy perfectly. But a final unsettling question remained. It wasn't about what the Americans had built, but how. As they reviewed their collective findings, a single overarching theme emerged: a ghost in the machine that was more powerful and more terrifying than any single piece of technology. It was the physical manifestation of the American philosophy of mass production. This was not a craftsman's airplane. A Messerschmitt or a Focke-Wulf was the product of a master-apprentice tradition where skilled workers hand-fitted components to exacting but often idiosyncratic standards. The result was a high-performance machine, but also one that was difficult and time-consuming to build and repair. The Thunderbolt was different. It was a product designed from the outset, not just for performance, but for production. Every decision seemed to have been made with an eye toward the assembly line. They saw it in the use of castings instead of complex forgings, in the standardized fasteners in the modular components like the engine and the wiring harnesses. An engineer who had previously worked for Opel, a subsidiary of General Motors, recognized the logic immediately. "This is not an aircraft," he said, gesturing to the blueprints. "This is a Chevrolet. It is designed to be assembled by semi-skilled workers quickly and in immense numbers. The parts are designed to be interchangeable, not just within one aircraft, but across thousands of them." This realization was a paradigm shift. The German team had always prided themselves on their superior technique, their engineering prowess. But they were now confronting a different kind of genius, the genius of logistics and systems engineering. The Americans weren't trying to build the single best fighter in the world. They were building a good enough fighter, and they were building it on a scale that Germany could not comprehend. The numbers were readily available from intelligence reports, but they had always seemed like abstract propaganda. Now, holding the physical components in their hands, the numbers became terrifyingly real. Republic Aviation was producing these complex machines at a rate of over 500 per month from a factory in Evansville, Indiana, a factory that hadn't even existed 2 years prior. The total production would eventually exceed 150,000 units. Germany, in its best year, produced around 11000 FT-190 seconds of all variants. The engineers began to see the P-47 not as an isolated weapon, but as a single component in a vast, interconnected industrial war machine. The high-quality alloys in the turbocharger were a product of America's control over global resources. The reliable engine was a product of a mature automotive industry that had perfected the art of mass-producing complex machinery. The endless supply of .50 caliber ammunition was the output of arsenals that operated on a scale that made German arms factories look like cottage industries. They were not fighting Republic Aviation, they were fighting the full focused might of the Ford Motor Company, General Electric, Pratt & Whitney, and 1,000 other subcontractors all working in concert. This ghost in the machine explained the American tolerance for waste and crudeness. The round-headed rivets were a trade-off, a marginal loss in aerodynamic performance for a massive gain in production speed. The heavy armor was a trade-off, a penalty in agility for a higher rate of pilot survivability, ensuring that the huge investment in pilot training was not lost on a pilot's first few missions. The entire design was a series of pragmatic industrial compromises aimed at a single strategic goal: to put as many durable, lethal, and repairable weapons into the field as possible and to keep them there. Dr. Richter summarized the finding in a draft of his final report. The P-47 Thunderbolt represents a victory of the production engineer over the aeronautical designer. It is a weapon that could only be conceived and produced by a nation that believes industrial capacity itself is the ultimate strategic weapon. We have concluded that our focus on achieving the peak of performance in individual units, while laudable from a technical standpoint, is strategically insufficient when faced with an enemy capable of producing overwhelming quantities of good enough equipment. This was the ultimate soul-crushing discovery. Germany's greatest strength, its engineering excellence, was being rendered irrelevant. They had brought a finely crafted sword to a gunfight, and the gun was being fed by an endless belt of ammunition. Now came the most difficult task of all. They had to deliver this unwelcome news to a high command that was still intoxicated with the myth of its own technological superiority. The atmosphere in the conference room at the Reich Air Ministry in Berlin was thick with cigar smoke and self-assurance. It was early December 1943, and Reichsmarschall Hermann Göring had convened a meeting of the Luftwaffe's senior leadership, including General Feldmarschall Erhard Milch, the head of aircraft production, and General der Jagdflieger Adolf Galland, the charismatic and respected commander of the fighter arm. The agenda was a review of enemy aircraft technology. It was meant to be a routine meeting, a confirmation of German superiority. Dr. Klaus Richter and Dr. Hans-Georg Schmid from the Rechlin Test Center stood stiffly at one end of the long oak table, their detailed report on the captured P-47 Thunderbolt feeling impossibly heavy in their hands. They were not warriors returning with tales of victory. They were messengers bearing a prophecy of doom, and they knew it would not be well received. Richter began the presentation, his voice steady but devoid of emotion. He projected slides showing the P-47's components, detailing their findings on its structural strength, its armor, its resilient engine. Göring, lounging in his oversized chair, listened with growing impatience. Yes, we know, he interrupted, waving a dismissive hand. It is a truck, a flying farm tractor. Our pilots are shooting them down like partridges. What is the point of this, Richter Galland? A pilot's pilot remained silent, his eyes fixed on the images, a thoughtful frown creasing his brow. He had heard the stories from his men, both the laughter and the growing whispers of concern. Then Richter moved to the heart of the matter, the turbo supercharger. He explained the system in detail, showing diagrams of the complex ductwork, the intercoolers, and the turbine itself. He presented the performance charts showing how the P-47 maintained its power at altitudes where the Fu-190A began to suffocate. Reichsmarschall Richter said, his voice gaining urgency, this system gives the American fighter a decisive performance advantage above 8,000 meters. We have concluded that our current fighters cannot effectively engage it at the bomber's operational altitudes. A murmur went through the room. This was no longer a discussion of a clumsy aircraft. It was a direct challenge to the Luftwaffe's ability to defend the Reich. Göring's face flushed with anger. Impossible. German technology is the best in the world. You are telling me these gangsters and cowboys have out-engineered us. They build refrigerators and automobiles, not high-performance aero engines. Dr. Schmid then stepped forward to present the most damning evidence. It wasn't about the design. It was about the materials. He passed around a sample of a turbine blade from the GE Turbo. This alloy, gentlemen, he explained, is composed primarily of nickel and cobalt, with traces of tungsten and chromium. To mass-produce this single component, the Americans are using more cobalt than our entire Reich has available for all aircraft production for the next 6 months. We cannot replicate this system not because we lack the knowledge, but because we lack the raw materials. The room fell silent. This was a truth that could not be dismissed with bluster. It was the cold, hard logic of geology and global economics. America, with its vast domestic resources and its control of global supply chains, was fighting a different war. While Germany was forced to develop complex synthetic materials, America was simply digging the real thing out of the ground. Galland finally spoke, his voice quiet but carrying immense weight. The pilots are seeing this, he said. They call it boom and zoom. The Thunderbolts stay high where we cannot reach them effectively. They dive with an impossible speed, they fire, and they are gone back up into the sun. My men are brave, but they are being asked to fight a vertical battle with a machine that is a better climber at altitude and a faster diver. You cannot defeat physics. The final part of the report detailed the production philosophy, the mass-produced, standardized, easily repaired nature of the aircraft. It concluded with the chilling projection that America was on track to produce more P-47 seconds in the next year than the total number of single-engine fighters the Luftwaffe had in its entire inventory. The report was an indictment not of German pilots or even German engineers, but of the entire strategic foundation of the Third Reich. It was a nation built for a short, sharp blitzkrieg, now trapped in a protracted war of industrial attrition against an opponent whose capacity to produce was seemingly limitless. Goering, his rage turning to a sullen pout, dismissed the engineers with a wave. The meeting was over, but for the men in that room, the comfortable illusion of technological superiority had been shattered forever. They now knew the truth. They were not just losing a battle for the skies, they were losing a war against the factory. And as the engineers left the ministry, they knew that even with this new terrifying knowledge, there was very little the Reich could actually do to stop the storm that was coming. The revelations from the captured Thunderbolt sent a shockwave through the German aviation industry, but it was a shockwave that produced more paralysis than action. The uncomfortable truth, as laid out by the Rechlin engineers, presented a problem that could not be solved with a clever new design or a brilliant tactical innovation. It was a systemic crisis, a fundamental mismatch between Germany's capabilities and America's reality. The immediate reaction from some within the high command was predictable. If the American design is effective, then we must copy it. Orders were drafted to begin a crash program to reverse engineer the General Electric turbo supercharger. But this effort was doomed from the start, a perfect illustration of the futility of Germany's position. The engineers at BMW and Daimler-Benz, brilliant as they were, could not simply conjure up the necessary materials. The turbine blades of the American turbo were not just made of metal, they were made of a specific resource-intensive recipe. Germany was already facing critical shortages of nickel, cobalt, and chromium. These materials were essential for everything from tank armor to machine tools. Diverting the massive quantities needed to mass-produce turbo superchargers for thousands of fighters would mean crippling other vital sectors of the war economy. It was a strategic, Sophie's choice: would they have high-altitude fighters or would they have panzers? They could not have both in the quantities needed. America, on the other hand, never had to make that choice. Its industrial might allow it to have everything all at once. Even if the materials had been available, the manufacturing challenge was insurmountable. The American system was built on a foundation of specialized machine tools and a vast network of subcontractors, each an expert in a specific component. Germany's industrial base, by contrast, was being systematically dismantled from the air by the very bombers the P-47 seconds were designed to escort. A new production line for a complex system like a turbo supercharger would take months, even years to establish. By the time the first German-made turbo came off the line, the war would likely be over. The attempt to imitate was a strategic dead end. The more pragmatic approach championed by designers like Kurt Tank at Focke-Wulf was not to copy the American solution, but to develop a unique German answer to the problem of high-altitude combat. This effort produced some of the most advanced piston engine fighters of the war, notably the Focke-Wulf Ta-152. The Ta-152 was an aeronautical masterpiece, a long-winged high-performance interceptor specifically designed to kill Allied bombers and their escorts in the thin air of the stratosphere. It used a powerful Jumo 213E inline engine with a two-stage, three-speed mechanical supercharger and a system for injecting a methanol-water mixture for emergency power. On paper, and in the hands of a skilled pilot, the Ta-152 was superior to the P-47 at extreme altitudes. It was faster, more agile, and better armed. It was the perfect expression of the German engineering philosophy, a highly specialized, technically exquisite weapon designed to solve a specific tactical problem. But the Ta-152 was also the perfect symbol of Germany's strategic failure. It was too complex, too resource-intensive, and it arrived far too late. While America was churning out thousands of P-47 seconds every month, Germany struggled to produce a few dozen Ta-152 seconds. The factories needed to build it were being bombed, the supply lines for its specialized components were cut, and there were not enough experienced pilots left to fly it effectively. For every single Ta-152 that reached the front, the Allies could field 100 Thunderbolts or Mustangs. The Ta-152 was a perfect solution that could never be implemented on a meaningful scale. It was a beautiful final flourish from a dying industry. The engineers at Rechlin watched these developments with a sense of grim vindication. Their report had predicted this outcome. They had seen firsthand that the American advantage was not in a single piece of technology that could be copied, but in the entire system that produced it. They understood that the war in the air had ceased to be a contest between individual pilots or even individual aircraft designs. It had become a war of production statistics, of logistics, of raw materials. And in that war, Germany was hopelessly outmatched. The laughter and arrogance of early 1943 had evaporated, replaced by the quiet, desperate work of engineers trying to hold back an industrial tide with increasingly sophisticated but ultimately futile technological sandcastles. While they labored in their design offices and laboratories, grappling with the impossible reality of their situation, the theory they had discovered on their dissection tables was being proven day after bloody day in the skies over the Reich. The pilots who had once mocked the milk jug were now facing the terrifying kinetic reality of what it had become. While the engineers at Rechlin were writing reports and the German high command was wrestling with uncomfortable truths, the pilots of the U.S. Army Air Forces were busy rewriting the rules of air combat over Europe. The early fumbles and costly lessons of the spring of 1943 had given way to a brutal, systematic application of the P-47's unique strengths. The transformation was led by commanders like Colonel Hubert Hub Zimke of the 56 Fighter Group, a brilliant and ruthless tactician who had quickly realized that trying to fight a traditional dogfight in a Thunderbolt was suicide. The doctrine he and other leaders developed was simple, direct, and utterly lethal energy is everything. The American pilots were drilled relentlessly. Maintain altitude discipline, never follow a German fighter down into a turning fight where he has the advantage. Use your superior weight and power to dictate the terms of the engagement. The tactic which became known as the boom and zoom was the practical application of the engineering principles the Germans had just discovered. A typical mission would see the P-47 seconds climbing to 30000 feet or higher, positioning themselves above and between the bomber streams and the sun. From this perch, they were effectively untouchable. German fighters attempting to climb up to engage them would be slow, sluggish, and vulnerable. When a formation of Luftwaffe interceptors was spotted below the American, flight leader's command would crackle over the radio. The execution was a marvel of coordinated violence. The heavy Thunderbolts would roll over noses, pointing toward the earth, and plunge downwards. The laws of physics took over. The 7-ton aircraft, already possessing immense potential energy from its altitude, converted it into kinetic energy with terrifying efficiency. Their airspeeds would climb past 450,500, sometimes approaching 550 miles per hour in a controlled dive. To the German pilots below, they appeared as if from nowhere, diving at angles and speeds that seemed to defy the limits of a propeller-driven aircraft. Evasion was nearly impossible. By the time a German pilot registered the threat, the P-47 was already in firing range. Then came the sound that German pilots began to dread more than any other, the percussive roar of Roosevelt's buzzsaw. For 2 to 3 seconds, a concentrated stream of over 200 half-inch armor-piercing incendiary rounds would slam into the German aircraft. The effect was absolute. FO 190 seconds and BF 109 seconds aircraft that pilots had trusted with their lives would simply cease to exist, shedding wings, tails, and engines as the hail of 50 caliber fire tore them to pieces. And then as quickly as they had arrived, the Thunderbolts were gone. Using the immense speed built up in the dive, they would execute a zoom climb, converting their kinetic energy back into altitude, pulling up and away from the fight, ready to set up for another devastating pass. A German pilot who survived the initial onslaught was left with an impossible choice. Try to climb after the departing P-47 seconds, a slow and futile effort, or disengage from the bombers and dive away, conceding the sky to the Americans. The psychological impact on the Luftwaffe was catastrophic. The confidence of 1943 was replaced by a gnawing dread. The P-47, the once ridiculed Milchkrug, was now known by a new, more fearful nickname, the Indianerschreck, the terror of the Indians, a derogatory German term for the Americans. German aces, veterans of hundreds of battles, found themselves helpless. Major Heinz Baer, an ace with over 200 victories, described an encounter. You don't see them until it is too late. They come down out of the sun like lightning. There's a roar and the sky is full of tracers. My wingman simply exploded. He never made a radio call. He was just gone. You cannot fight something you cannot see, and you cannot escape something that is faster than you. The tactics worked so well that by the spring of 1944, the Luftwaffe was actively avoiding combat with P-47 seconds at high altitude. They had learned through brutal, bloody experience that engaging the Thunderbolt on its own terms was a death sentence. The theory discovered in the sterile, quiet hangar at Rechlin had been proven in the crucible of combat. The brute force design, the resilient engine, the high-altitude turbocharger, and the overwhelming firepower had combined to create not just a fighter, but a perfect system of destruction. This tactical dominance, however, was not an end in itself. It was the key that unlocked the door to Germany's ultimate strategic defeat. The tactical mastery achieved by the P-47 pilots in late 1943 and early 1944 was not just about winning individual dogfights or racking up impressive kill ratios. Each diving attack, each shredded Messerschmitt was a hammer blow against the very foundation of Germany's ability to wage war. The strategic purpose of the American escort fighters was twofold. First, to protect the heavy bombers of the 8th Air Force, and second, to systematically annihilate the Luftwaffe fighter arm through a brutal war of attrition. The P-47, with its unique blend of firepower and survivability, proved to be the perfect instrument for this task. As the bomber streams pushed deeper into Germany, striking at the heart of the Reich's industrial capacity, the Luftwaffe had no choice but to rise and fight. And every time they did, they were met by the Thunderbolts. The period known as Big Week in February 1944 marked the turning point. For 6 consecutive days, the 8th Air Force launched massive raids against German aircraft factories, hoping to deliver a knockout blow to Luftwaffe production. The German fighter force rose to meet this challenge with everything they had, throwing their best pilots and machines into a desperate defense. The result was a slaughter. The P-47 seconds and their long-range P-51 Mustang stablemates tore into the German formations. In that single week, the Luftwaffe lost nearly 400 fighters and, more critically, over 100 of its experienced veteran pilots, men who could never be replaced. The American losses, while significant, were a fraction of Germany's and were quickly replaced by the endless stream of new aircraft and freshly trained pilots arriving from the United States. The mathematical logic that the Rechlin engineers had discovered was now playing out on a strategic scale. With the Luftwaffe's fighter arm broken, the sky over Germany effectively belonged to the Allies. The B-17 seconds and B-24 seconds could now roam with near impunity, systematically destroying oil refineries, ball-bearing plants, and transportation hubs. German war production, which had miraculously increased under Albert Speer's leadership, began to falter and then collapse. The panzers on the Eastern Front ran out of fuel. The new jet fighters couldn't fly for lack of parts and pilots. The German war machine was being starved to death from the air. This air supremacy, bought with the blood of Allied aircrews and secured by fighters like the P-47, was the essential precondition for the success of Operation Overlord, the D-Day landings in June 1944. When Allied troops stormed the beaches of Normandy, they did so under a sky completely dominated by Allied aircraft. The Luftwaffe was a non-factor, unable to effectively attack the invasion fleet or the beachheads. In the aftermath of the landings, the P-47 transitioned from a high-altitude escort to its most feared role, the fighter-bomber, the dreaded Jabot. Armed with bombs and rockets, Thunderbolts roamed the French countryside, creating a no-fly zone for the German army during daylight hours. They destroyed tanks, truck convoys, trains, bridges, anything that moved. A German soldier from the Panzer Lehr Division described the experience: "We could not move during the day. If a single truck tried to use a road, the Jabots would be on it in minutes. They came in low, ignoring our flak, their guns ripping everything apart. It was not a fight, it was a hunt. We were the prey." The P-47 had become the steel-fisted enforcer of Allied air power, ensuring that German reinforcements and supplies could never reach the front in time to stop the Allied breakout from Normandy. The teardown at Rechlin had been an autopsy in advance. The German engineers had looked inside the American machine and seen a reflection of their own nation's impending doom. They saw a philosophy of warfare that they could not match, built on a foundation of industrial power that they could not hope to equal. The P-47 was not merely a superior weapon in certain respects. It was the product of a superior war-making system. It represented a new paradigm where victory was achieved not through the heroic actions of a few aces, but through the systematic, overwhelming application of industrial force. The final bitter irony for the engineers was knowing that their own brilliant work, their elegant and advanced designs, were ultimately irrelevant in the face of this new reality. They had built a better sword only to be confronted by an opponent who had invented the firearm and was manufacturing it on an assembly line. In the final chaotic months of the war, as Allied armies closed in on Berlin from both east and west, the P-47 Thunderbolt flew its last combat missions. The dinosaur that Alexander Kartveli had envisioned had not only survived, it had become the apex predator of the European sky. It had outlasted its critics, confounded its enemies, and carved a unique and brutal legacy into the history of aerial warfare. It was never the most beautiful fighter, it was never the most agile, but in the war, it was built to fight a war of industrial attrition. It may well have been the most effective. Its story is the story of how America won the Second World War, not through elegance or finesse, but through overwhelming intelligence and utterly relentless power. After the surrender, Allied intelligence teams swept through Germany, securing research facilities, interrogating scientists, and collecting the artifacts of the defeated Reich. At the captured Rechlin test center, they found the meticulous reports and blueprints detailing the German analysis of Lieutenant Miller's captured Thunderbolt. The documents were a testament to the thoroughness of German engineering, but they were also a profound admission of defeat. The final summary, written by Dr. Richter himself, was a sober and unsparing epitaph for the Luftwaffe's technological pride. "We misjudged the enemy because we judged him by our own standards," he wrote. "We saw a lack of elegance and assumed it was a lack of sophistication. We were wrong. The P-47 is not a fighter aircraft in the European sense. It is a flying artillery platform, a survivable and mass-producible delivery system for an overwhelming amount of firepower. Its design represents a philosophy of total industrial warfare that we were unprepared to face." The men who had flown against it echoed that sentiment. General Adolf Galland, in his post-war memoirs, wrote with the grudging respect of a seasoned warrior, "The Americans knew that in a long war, the machine that can take punishment and bring its pilot home is more valuable than the one that achieves a fleeting performance advantage. The P-47 could be hit by cannon and still fly. The Bf-109, if it took a hit in its cooling system, the pilot had 10 seconds to decide where he wanted to crash. We underestimated the P-47, and we paid a terrible price for that mistake." The dinosaur had proven not only to have good proportions, but to be perfectly adapted to its environment. The legacy of the Thunderbolt extends beyond the battlefield. It was a machine that embodied the American character of the era. Big, loud, powerful, a little rough around the edges, but incredibly tough and effective when it mattered. The very systems that made it a great weapon of war also helped shape the post-war world. The Pratt & Whitney R2800 engine went on to power a generation of commercial airliners, helping to build the modern age of air travel. The advanced metallurgy developed for the turbo supercharger found applications in jet engines and industrial turbines. The philosophy of mass-producing complex, reliable systems became the hallmark of American industry for decades. The P-47 was a weapon of war, but it was also a product of peace, a testament to what a free, democratic, industrial society could achieve when mobilized for a common purpose. It was not built by slaves or driven by a fanatical ideology. It was built by ordinary men and women, the gangsters and cowboys Goering had so arrogantly dismissed, who came together to forge the arsenal of democracy. In the end, the story of the German engineers and the captured Thunderbolt is a cautionary tale. It is a story about the danger of arrogance, the folly of underestimating an opponent, and the profound truth that wars are won not just by brave soldiers, but by the logisticians, the engineers, and the factory workers who support them. The German engineers who took apart that P-47 inches, Hangar 5, were brilliant men, masters of their craft. But as they stared into the heart of the American machine, they were forced to admit they were facing a power they could not match, a force that rendered their own exquisite genius tragically obsolete. They had looked for weakness and found a strength they couldn't comprehend. They had searched for flaws and found a philosophy that would ensure their defeat. They had expected to dissect a milk jug, and instead they had uncovered the secrets of a thunderbolt.